Time dilation is part of the amazing 1905 theory of special relativity, which was, you guessed it, put forth by Einstein. But before we get to all that stuff, I have a quick question. Is the car here moving or is the ball moving? The answer is, it depends on your reference frame. If you went along with the ball, you'd see the car move. And if you sat inside the car, you'd see the ball move. If I had a tree, and if we sit on a tree, we see both move. Who's really moving? That's a meaningless question because motion depends on what the observer sees. To make more sense, think about it. If you're in a chair all nice and comfy, are you moving? To the person on another chair in the same room, you're not. But to someone on the sun, you are. That's because the earth is flying around the sun at incredible speeds. So is the sun at rest? No, the sun is also moving with respect to someone in another galaxy. So on and so forth. I hope you get the idea. This idea of meaninglessness of motion without reference frames is central to Galileo's idea of relative motion. No, not that kind of relative. According to this, there is no absolute motion or motion with no reference frame. Now, there's something else in electromagnetism which states the speed at which light moves through empty space is constant in all reference frames. But as we saw in relative motion, motion varies from reference frame to reference frame. You might think that either one of these ideas was wrong, but they both have been experimentally verified to large extents. So the only solution would be to make these ideas compatible with each other. This is where the genius of Einstein comes in. Let's construct a light clock. It works by letting a beam of light bounce off one mirror only to bounce onto another, where it bounces back to the first in a continuous cycle. Let's say the time taken by light to bounce off one mirror onto another and back again as t seconds. Let's take two such light clocks with different colors and place them on two spaceships, spaceship A and spaceship B. Let's say A moves uniformly with respect to B. Remember, both light clocks measure the same time t seconds, so the beam of light travels up and back down in the same time in both ships. But doesn't this disobey the constancy of the speed of light? I mean, a person standing in B would see the light on A cover a larger distance than the one on B in the same amount of time. The beam on A appears to travel in an additional horizontal distance along with the original vertical distance that the beam on B travels with. Speed is equal to distance upon time. So if time remains the same, but if distance changes, speed changes. If distance increases, speed increases. Wait, what if we increase time as well as distance by a particular amount? According to math, we should have the same speed. So constancy of the speed of light would be maintained. But we know that the clocks tick t second ticks, right? So does that mean t seconds on board A would appear differently to someone aboard B? If you think about it, with respect to B, time would be slower on A. If we slow down the beam on A to match the speed of the beam on B, we find t seconds passes slower on A. I know it isn't intuitive, but that's only because we aren't used to seeing this. I'm going to derive an equation that describes time dilation, and what's more important than the equation is that you understand why it happens, how the equation works. We will take our light clock and place it aboard a spaceship. Our friend Leslie the astronaut decides to be our onboard observer. Let's consider the distance between the two mirrors of the light clock as h. Therefore, the distance covered by the beam in one tick is 2h because the beam goes up and comes back down. According to Leslie, the tick of the light clock is delta t. According to Leslie, the tick of the light clock is t seconds. We know speed is equal to distance upon time. Rearranging for time, we get time is equal to distance upon speed. So we can write that as t is equal to 2h upon c, where 2h is the distance covered and c is of course the speed of light. You are not aboard the ship, and the ship is traveling a velocity v relative to you. So you should see the beam of light cover a horizontal distance along with its vertical tick. When the light hits the top mirror from the bottom, let's say the rocket moves ahead a distance L, and when the beam strikes the mirror at the bottom, the rocket moves another distance L. So the total horizontal distance covered by the rocket and the beam of light relative to you is 2L. Let's call the distance light covers from one mirror to another as m. Just as we did in the first case for Leslie, the time you observe, let's call that delta t is 2m upon c. What we observe is that c is a common denominator in both case equations. So since 2h is less than 2m, we can conclude that you observe the light beam takes a longer time to tick. Longer time means time slows down according to you. Okay, what can we say about m? If you study the Pythagorean theorem, we can write m square is equal to h square plus l square, since m is the hypotenuse of this triangle. If we take the square root of both sides, we get m is equal to the square root of h square plus l square. Note that we can denote the square root by half. Now let's multiply both sides of this equation by 2. Now I want you to think about what L is. L is the distance the rocket goes in the time you measure delta t multiplied by the speed of the rocket as we see it, which is v, divided by 2. Therefore, we can write L is equal to v into delta t upon 2, and replacing L in the equation, we get 2m is equal to 2 into the root of h square plus v into delta t upon 2 the whole square. Now 2m, that is the distance light travels in our time interval delta t, can be written as c into delta t, that is speed into time. Now let's solve for delta t. Let's square both sides. Squaring both sides, we get c into delta t the whole square is equal to 4 into h square plus v into delta t upon 2 the whole square. Now let's distribute that 4. Therefore, we get c into delta t the whole square is equal to 4 into h square plus 4 into v square into delta t square upon 4. Let's cancel that 4 and 4. Now let's subtract v square into delta t square from both sides of the equation. Let's factor delta t square from the term on the left. Therefore, we get c square minus v square the whole thing into delta t square is equal to 4h square. Now let's divide both sides of this equation by c square minus v square. And what does that give us? That gives us delta t is equal to 4h square upon c square minus v square. Okay, let's find the square root of both sides. So what does the equation become? It becomes delta t is equal to 2h upon the root of c square minus v square. Now let's multiply and divide the radical by c square. And what does that give us? Well, we can find the square root of that c square, and well, of course that's c. So let's take that c out and distribute the denominator for both terms in the numerator. So what does that leave us? C square upon c square minus v square upon c square. Well, we know c square upon c square is equal to 1. So let's just write that as 1 minus v square upon c square. But 2h upon c is nothing but the time that passes on the ship according to Leslie, which is denoted by capital T. Which we denote by capital T. Therefore, substituting the value of 2h upon c, we get delta t is equal to t upon the root of 1 minus v square upon c square. And that is the equation of time dilation, where delta t is the dilated time, t is the time that passes for the object that is relatively moving, v is the relative motion, is the relative speed of the ship, and c is of course the speed of light. I hope this video gives you a clearer and more intuitive understanding of time dilation. Thank you for watching this video.